We're going to look at electronic configurations. When we do electronic configurations, the rules we teach you are for the ground state. The exceptions we teach you are for the ground state. Anything that does not follow the rules and is not one of the exceptions ends up being what we call the excited state. But the ground state is when we follow the Aufbau principle. The excited state would be if we absorbed a photon of light of just the right energy and put one of the electrons higher than it should normally be in the ground state, we call that the excited state. Cool? So for ground state electronic configurations, you just start filling in electrons. If you look at how many electrons an element has, we're just going to fill them up on this diagram till we're done. But the order gets a little bit funky. What comes after 1s? 2s, then 2p, then 3s, then 3p? No, then 4s comes before 3d. That's where things get a little confusing. So the order.
I always like draw the minus sign.
Exactly. And so that's what we're going to do. It's easier to remember the order if you just kind of think about it in terms of the periodic table, because you'll always have one in front of you. This is not the only convention, but because I know you'll always have a periodic table, it's my favorite. Every element, we go up in atomic number. As long as we're talking about neutral species, we not only gain a proton in the nucleus, we gain an electron. And so we can think of every element as representing that additional electron it just gained. And so hydrogen and helium, the first two electrons, if you will, that we're representing, are in the 1s. And so for this convention, helium would really belong over here, just an FYI. What comes after helium? Lithium. And lithium and beryllium would correspond to the electrons in the 2s subshell. And so it turns out everything is grouped on the periodic table in blocks. This is the S block right here. Sodium and magnesium 3s, potassium and calcium 4s, rubidium and strontium 5s, so on and so forth. Cool. After beryllium, what do we got? Boron, and boron through neon. So beryllium gets us through 2s. Boron through neon are the 6 electrons we're filling into the 2p's. And so we refer to the elements over here as the p block. We got the 2p, the 3p, the 4p, the 5p, 6p. Cool. So, and again, so 1s, then 2s, then 2p, then 3s, then 3p, then 4s. But between 4s and 4p, we got a big row of transition metals here. And the transition metals are a little slow. And they got to the periodic table a little bit late. And so they're a row behind. In between the 4s and the 4p are the 3d. So it turns out the 4s, even though it's a higher shell, are on average lower in energy than the 3d. Cool? And then so on and so forth. We'd have the 4d between 5s and 5p. We'd have the 5d, and then down here, which you guys don't really have to worry about too much, that's where you'd actually have the 4f and the 5f, and I'm not going to bring those up again. Cool, because you guys only got to know up through zinc, who's right here as far as electron configurations go. So that's what I'm going to focus on. So let's start small here. Let's just say we have fluorine. Want the electron configuration, starting from the beginning. And how many electrons are in there? 2. Sweet. 1s2. Ooh, what comes before 2p? Good. And notice, because it's 1s, and then 2s, and then 2p. So, cool. 2s2 then. And 2p, but we're not going to fill them up because fluorine's right there. In fact, we can go look at fluorine right over here, right? So 2p, 1, 2, 3, 4, 5. Cool, and that's the electronic configuration in the ground state for fluorine. So, Colleen, would you want to come up and put uranium's electron configuration on the board? I didn't think so. Nobody wants to, and I don't want to put it on the board either. No, you really don't, Natalia, I guarantee it. So it's awful.
You don't know me.
It would be, yeah, it would be super long. And so we've come up with a shorthand because we have these super long ones, even though you guys don't have to know the super long ones. So, and the way it works, if we look at fluorine, on your way to fluorine from 1s2 to 2s2 to 2p5, what was the last noble gas we crossed? The only one we crossed, helium. And so right here, that represents helium, 1s2. And so instead of writing it, we'll simply write helium in brackets, 2s2, 2p5. Did we really save a whole lot of time by doing this? Not this one. Would we have saved a lot of time if we were doing this for uranium? You bet. So for the bigger ones, this becomes a big issue. We call this the noble gas configuration. And the bigger the element, the more time this saves for us. Didn't accomplish much here, but later on it definitely would. So let's make this a little harder. Let's go potassium. So give me the overall electron configuration first, and then we'll go noble gas. So start me off. Well, they all start off in the same place, 1s2, and then 2s2, and then 2p, and we'll fill it up. Where's potassium on this list, by the way? Potassium right there. Oh, we're coming back. Noble gas configuration we'll do a second. So 1s2, 2s2, 2p6. What's after the 2p6? 3s2, and what comes after the 3s? 3p. Fill it up. Cool, what's next? Good, and we're stopping at only one electron in the 4s because that's where potassium is. Now, good. All that can be summed up by simply saying argon, 4s1, we call that the noble gas configuration. If they ask you for the noble gas configuration, these are both correct. So you got to... Oh, for the 3p's? Cool. So for the 3p's, represented right here. So first of all, if we did it here, you'd have an easier time, right? 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6, 3s2, 3p, 1, 2, 3, 4, 5, 6, and then 4s1 for potassium. But the way you recognize that off the periodic table is, again, hydrogen, helium, 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6, 3s2, 3p, 1, 2, 3, 4, 5, 6, 4s1 for potassium. Awesome. For the 3D, we just want one big orbital. Awesome. No worries. I'm actually happy about that. So what would be the difference between fluorine and the fluoride ion?
Okay, fluoride ion has one extra electron.
Yeah, negative charge means you have extra electrons. So -1, 1 extra, -2, 2 extra, so on and so forth.
So that would be 1s2, 2s2, 2p6. So would you be able to just write that in order? It's helium. Is my other question.
1s2, 2s2, 2p6, and no, you wouldn't, because you'd need to write it the same thing as neon, I think is what you meant to say.
Yeah, that's what I meant. Sorry.
Sweet.
Yeah. So can you actually?
Somebody told me earlier that the operator was never wrong. I was checking. I don't know.
Can you actually do that? Well, on a
Yeah, oh no, these are both correct for F minus. Totally both correct. Cool. So same thing. Potassium, most common ion is +1. What do I do here? Yeah, it's the same thing. One way to do it is just to say AR, because you lost an electron. Positive ions, you lose an electron. So what if I have something like nickel? Transition metals suck. So where's nickel on this game?
transition metals number 28.
Good, number 28, right there. And so where do we end for nickel? In what section?
The 3Ds.
Yeah, we are totally going to end in the 3Ds. And if we count them off, we can say 1, 2, 3, 4, 5, 6, 7, 8. So I know it's going to end in 3D8. If I look at my answer choices and there's only one that says that, great, I'm done. Right? Life is good. So but let's do the whole thing. In fact, let's just do the noble gas configuration. What's the last noble gas we crossed before nickel? Good, argon. And then what do I say? Potassium and calcium represent 4s2. And then what do we say it was going to end with? 3d8. Now what if I have nickel 2+.
You would fill up the,
Don't.
take the S. No, you.
So first of all, do I need to add or remove electrons?
No, remove.
Good, I need to remove 2 electrons. That's why we're positive. We lost 2 negative charges.
It would be AR4, it would actually just be AR3D10, right? Because it won't-
So here's the deal. With the transition metals, the rule is this. When you remove electrons, you always remove them from the highest shell first. What's a higher shell? Shell 4 or shell 3?
4, sorry.
4 is a higher shell number. So we're going to remove the 4s before we actually remove the 3d. And that's weird because they weren't the last ones we filled in, but they are going to be the first ones we remove. You were right. So in this case, those are the 2 electrons I remove, and I'm just going to be left with argon 3d8.
Oh, there was no 10.
Right, it wasn't 10, it was 8, but yeah. So in this case, this is not necessarily an exception. The rule just says remove from the highest shell number first. Now the exceptions, though. So copper and chromium, 2 standard exceptions. In their ground state configuration, if you follow the normal rules, you'll get it wrong. So let's follow the normal rules and then let's correct them. If I do the noble gas configuration for copper, what am I going to get? Oh, noble gas. And then? And what would I get for chromium if we just followed the rules as well? Also in the no transition metals there. Good. Well, it turns out if these are exceptions, then obviously just following the rules means these are wrong. So that's the first part. These are not the ground state configurations for chromium and copper. It turns out copper knows something we didn't. That we've talked, we're going to talk a little bit later about having a filled octet and things of this sort, and that's really stable to have a filled octet. Well, it's not just stable to have a filled octet, it's stable to have a filled shell or subshell. So the octet's the filled shell, but even if you just end up with a filled shell, that's stable too. But that's not the only thing. Or if it's half full, that's a good place to be as well. So beyond the scope of why, for now anyways. So here's the deal. Copper's going to steal one from the 4s and put it in the 3d. And so the correct ground state electronic configuration for copper as an exception is argon 4s1 3d10. Why did we do this based on what we just talked about? Why does copper prefer this?
3D is a more stable shell than a 4S, and so it moves the 1 over to become more stable. See in the ending shell?
Sorta. So if you look, is the 4s full?
In that one?
In this one, in this
Oh,
one.
yes.
Yes. Is the 3D full? No. Is it exactly half full? No. So the 4s, that's good, but the 3D, it's not full or half full, that's no good. So here, is the 3D full?
Yes.
Yes. And the 4s is exactly half full, and that's good as well. And so it's a better overall electron configuration. It's lower energy than if you were to follow the rules. So this is the ground state electronic configuration for copper. What about for chromium then? What should be the exception now?
Because you can half fill both of them.
Yeah, if we bump one up here as well, we'll be half full. And both the 4s and the 3D subshells are half full. And so that's what chromium does. Cool. These are the only 2 exceptions you have to know. If you were in another class, it's not just copper and chromium. You'd have to know that it's copper, silver, gold, and chromium and molybdenum. And those are the 5 we require students to know. No, really. There are a bunch of exceptions.
How many?
A lot. But we don't expect students to remember them all. These are the ones we can make sense of. The other ones, it's kind of like, well, yeah, there's crazy patterns and stuff. But these are the only 2 that you guys have to know. Now, a couple last questions. Valence electrons, what's the definition?
Valence electrons are the electrons in the outermost shell of the electron configuration.
Good. Now, why do we call them? We have core electrons, we have the valence electrons, the outermost shell. Why do they get a special name? They can move. What do you mean? Yeah, they're the ones involved in making and breaking bonds. They're the ones involved in chemical reactions. They better get their own special name. The core electrons aren't involved. The valence ones are. So we got to talk about number of valence electrons. The number one's in the outermost shell. The way this works, group 1 metals, 1 valence electron, 2 valence electrons, 3, 4, 5, 6, 7, and 8 for the noble gases. That's the number of valence electrons. Let's see how that applies to something on here. It is the outermost shell. So for fluorine here, the 1s2, those are core electrons, but the 2s and 2p represent valence. And so for plain old fluorine, not F minus, but plain old fluorine, how many valence electrons?
5.
Again, it's the entire outermost shell.
Oh, so 7.
7. And just like we said, the halogen should have 7 valence electrons. Cool. What about for potassium? How many valence electrons? Much easier to see like this. 1 valence electron. Now here's where things are going to get a little bit tricky. Nickel, how many valence electrons? Yeah, here's the deal. It is indeed going to be 10. All 10 of these are considered valence. And here's the weird thing, because we're on shell 4, but we have to go back and fill some in from shell 3, and here's the deal. If shell 3, the 3Ds here specifically, if they're full, they're no longer considered valence, because then they're part of a previously filled shell. But if they're only partially full, not 10, any other number than 10, then they're still considered valence. We got 10 valence electrons right there. If you look at chromium, how many valence electrons for chromium? 6. Fantastic. Questions? Cool, let's see if you picked up the pattern. How many orbitals are there in an S subshell? Not how many electrons, but how many orbitals? Just in an S subshell. Notice when we do like 1s2, 2s2, that means 2 electrons, but how many boxes?
Oh, 1.
Just 1. So any S subshell has 1 orbital. What about a P subshell? How many orbitals are in any given P subshell?
No, 3.
It's 3. I erased them, but there were 3 boxes, which is why we can go up to 2p6. You can put 2 electrons maximum in any orbital in the universe, period.
Oh, 1, 3, 5.
Yes. So notice we go 1s2, 2s2, but 2p6. So the S's can only fit 2 electrons because there's only 1 orbital. But the P's can fit 6 electrons because there's 3 orbitals. The D's can fit 10 electrons because there's 5 orbitals. The F's can fit 14 electrons because there's 7 orbitals. So from S to P to D to F, it's 1 orbital, 3 orbitals, 5 orbitals, 7 orbitals. They count on the odd numbers.
I was just going to say, I think those might be one.
Turns out there's such a thing as G orbitals. Come after F. Guess how many there are? There are 9 of them. And how many electrons could you stick in those 9 orbitals? 18. Now let's look at this another way. In the first shell, all you have is the S. In the second shell, you have S and P. Third shell, S, P, and D. Fourth shell, S, P, D, and F. Fifth shell, S, P, D, F, and G, but we don't have any elements sitting there in the stable, but they do exist. So,
Like which one?
well, again, we know they exist, but we don't have any stable elements for them. But we could excite electrons up into them. So we do know they exist. Here's the deal. How many electrons can you put in the first shell? Actually, let's not even go there. How many orbitals total are in the first shell? I wish I had this still up here. All there is the 1s, 1 orbital. And it can hold 2 electrons, but 1 orbital. How many orbitals are there in the second shell? Well, there's 2 subshells, 2s and 2p, but how many orbitals are in the 2s?
1, 2, 3, 4, 5.
Well, there's 1 orbital in the 2s, but how many orbitals are in the 2p?
2. No.
3. And so how many orbitals are in the second shell?
4.
Total? 4. Great. Third shell, you have 3s, 3p, and now 3d as well. There's 1 3s orbital, 3 3p orbitals, and 5 3d orbitals for a grand total of 9. 1 orbital in the first shell, 4 orbitals in the second shell, 9 orbitals in the third shell. Guess how many in the fourth shell? 16.
Yeah.
It's always the number squared, the shell squared. So notice n squared equals the number of orbitals in a given shell. In the first shell, 1 squared, there's only 1 orbital. In the second shell, there's 4 orbitals total. In the fifth shell, there would be 25 orbitals total, including some of those G's we don't ever consider. All right, but if how many orbitals in the third shell? Let's go backwards. Well, how many orbitals in the third shell?
9.
There's 9. There's 9. 3 squared is 9. So we have the 3s, the 3p, and the 3d for a total of 9. But how many electrons maximum could be held in the third shell? Well, 9 orbitals can hold 18 electrons, 2 electrons per orbital. So we can take double n squared as being the maximum number of electrons in a shell. So if they give you a shell number and just expect you to calculate either the number of orbitals or the number of electrons maximum that could be held there, you have a quick calculation. Instead of being like, oh, in shell 3, what are there again? No, in shell 3, there are 9 orbitals and you can hold 18 electrons. Done. Simple calculation. Cool. Meant to say that earlier, forgot.